A couple of weeks ago, I posted a video on this book, The Sword, Form and Thought. And I talked a lot about the graphs that were contained within it and how I found them to be extremely interesting in their ability to describe the handling characteristics of a sword in a methodology that is mathematically and physically sound and is actually scientifically supported. This really made me excited to do this with my own collection and begin including these type of graphs in my reviews so you can begin to see how they may handle. Now, that is, I found out, a very monumental task because while you may not need a doctorate in physics, there is a lot of physics involved. And this book, as awesome as it is with all the graphs and a lot of the information, doesn't include kind of the underlying math behind everything. And even to this day, I can't say that I know 100% how they produced the graphs. But I believe that I've gotten close enough that I can replicate it with my own. So that's what this video is going to cover. I'm going to talk through the methodology for actually getting the information, getting the measurements on a sword, how you go about doing that, and then based on those measurements, being able to build these graphs. This is going to be a long video. I'm sorry, it just is. It's a really long topic, but I find it fascinating. And I linked in the description in the previous video all the interesting stuff by Johnsson and some of the interesting tidbits about this book and the concepts behind it. Similarly, I will be linking not only to that video in this video, but I'll also be linking to resources both that I have found in doing my research, as well as things that I have produced, so you, my viewing audience, can actually go do this yourself to some extent. And I hope I can make this a thing that people want to do, and maybe even make this a thing that manufacturers begin looking at, because the details of how a sword is made affects all of this. And I'll go over this in a lot of detail as we work through this. One of the things I do want to note, though, as I said, I couldn't reproduce 100%. I can get really close. In order to figure out at least some of the mechanics that they were using, I had to not really fudge numbers so much, but I had to figure out some of the measurements, such as force, that they might have been using that I don't know. They don't publish it in the book. And there are some constants that they do not reference, but they have to have as measurements that they used for every sword to maintain that consistency. So, in doing my research, I came across a paper by George L. Turner, and it's called The Dynamic of Handheld Impact Weapons. He did this back in 2002, I believe is when it was. It is published out of the Association for Renaissance Martial Arts. And my goodness, I had a hard time consuming this information. I've actually always been fairly good at physics. I was really good at it in school, but rotational physics always killed me. I could tell you linear motions all day long, but as soon as you started talking about rotational information, which the swords have everything to do with that, you had me at a loss a lot of times. So I had to do a lot of heavy research. So between that last video about this topic and this one, I have done just gobs and gobs of reading. And I have done reading outside of this paper, but this paper I think is the primary source, the very, very good source to point to and say, this is the information that I can use. So using that information from that entire research paper, there were only bits and pieces that were really actually pertinent to the handling characteristics of the sword. And at the very, very end of the paper, there was this kind of long process you could go through to get a lot of the measurements. Now, it's all the measurements to get something called moment of inertia. In this book, actually, they don't refer to it as moment of inertia. They refer to it as rotational inertia. Right here, rotational inertia. It's the same thing. When you say rotational inertia or moment of inertia, you're speaking about the inertia of a mass in a circular path. And George Turner had a way to actually get this information fairly quickly, which I'll go over in a moment. So I got the information there. I was able to pull out the information on how to get that inertia, but one of the bigger challenges, as I will talk to later, is that getting the angles correct. Building that model that has an angle that represents the magnitude of the moment of inertia through, basically zero, which is an acceleration, right? So you're taking that moment of inertia and you're turning it into what's essentially torque. And how that feels and turning that into a graph that makes sense is a really, really convoluted process. And again, there were constants necessary that are not covered in this book. So I had to recreate them. So that's going to be the first real segment of this video, is talking about how I recreated those constants. So I had an interesting task. How do I take the information provided in the book and the information that I can gather from this paper by George Turner and turn this into a practical methodology that's pretty quick and easy to do to be able to produce these interesting visual graphs? So what I found very, very quickly, and I have my tablet for all the notes in terms of terminology, is that I could very quickly get the sword's mass, what's called the period, which is, as you think of a pendulum, the period is time it takes to swing one cycle through and back. You can easily get the center of mass, or the point of balance. You can get the axis of rotation, which you can actually choose what that is, but you tend to use that as the crossguard on the blade side to make the pendulum swing, which I will cover in a little while. And you can get a lot of information just based on those couple of measurements. You can get a lot of information, including moment of inertia at that center of mass and moment of inertia at the axis of rotation, which are two very important things that you need to be able to note. Most importantly, that axis of rotation and the moment of inertia there, because based on that, you can build out an angular graph. What becomes really complex about this is was getting that information. So in the book, sword number 14 in the book, there was information about the sword and it had the graph. And I took these fancy little math tools, a little angular compass here, as it were, and a small tiny ruler. Transparency was absolutely necessary, and let me show you why. Because, and I'm going to walk really close to the camera here, but as I had to go through, and here it is, number 14, it's on page 35 of this book. This was the size of the sword that I had to base all this on. And as you can see, getting measurements, I needed to be able to have a very, very clear measurement system, because it's very small, and I had to be able to get it very, very precise. But using these things, I was able to get a couple pieces of information. I was able to gauge besides what they already had, I was able to gauge the angle of that part of the chart, the angle that the blade would follow through. And that gave me at least a target constant. Now, that would actually be a variable in every sword, but it gave me a target constant for this sword in order to try to figure out what the force was, because that angle is representative in some regards to angular acceleration. And angular acceleration times mass is the force in terms of rotational movement. So in order to recreate that, in order to understand that, using a lot of the information I'd already gathered based on the research of George Turner and what he presented, I was able to figure out that I had a sword that was very, very close to number 14. I actually kind of went through a lot of my collection and all the swords in that book to try to find one that would be simplistic enough and be close enough. And that was actually this one. The DSA Norman, so Dark Sword Armory. Now, I really like this sword. I talked about it a lot. And I thought it handled very well, which will be very interesting as we begin to look at some of the information on it. It is shorter. And length of everything matters, because if this was longer than the center of mass, that point of balance would actually change. So the change in things such as length and all that impact all the rest of it. The weight of the components of the crossguard, the weight of the blade, the taper of the blade, all this has to be very, very similar. And I think that this was very similar to number 14, albeit a little bit shorter. So based on that, I was able to get some of the measurements that I believe would be very similar to the measurements they would have been able to get on this kind of museum original. And the information that I got, and of course I will have all this handily right here, is that the sword's mass was actually only off by like not even a fraction of a gram. It's very, very similar in mass, which is 1.048 kilograms. And I will be doing all of this in the metric measurement system. It's absolutely necessary, actually. Doing it in pounds and things like that gets really convoluted. The period time, the time it takes for it to swing, and what that means is taking this in such a way that it will swing back. That's the time. So to get that measurement, you actually do it multiple times. You swing it like 10 times, and you have a stopwatch, and you show, okay, it goes through the swing. And based on that, I was able to get a period of 1.6 seconds. That's a rough estimation. The center of mass and axis of rotation are actually specific to the sword, although I think, again, they were fairly similar. That's 0.285 meters. So, you know, you really measure that in like centimeters, but everything needs to stay consistent in terms of, you know, the measurements that we're taking. Axis of rotation is 0.17. So what that actually means is the center of mass is, you know, way out here at the 0.285 measured from the pommel, and then 0.17 centimeters, which is, you know, basically 17 centimeters, right about here is where I had the axis of rotation. Sorry, it's right here on the blade side of the cross guard, is the axis of rotation. So axis of rotation here, center of mass over here. And then based on that, I can get a lot of interesting information about the sword. I can get the percussion point in terms of how far a percussion point is away from the axis of rotation. It's kind of a good indicator of where that center of percussion is. You can get the moment of inertia at the axis of rotation, which is an important piece of information. And then you can also use what is called the parallel axis theorem, which basically says you can actually do a really simple formula to shift the moment of inertia down to any point on the blade. And that includes the handle. So anywhere on the sword, you can actually shift down, do some basic math, and figure out what that moment of inertia would actually be. Based on this, that's actually the graph that you see at the bottom of these images, which is this kind of hump curve. A lot of interesting information comes from it, but essentially that curve is based strictly on that center of mass and its moment of inertia. And as you build out, using the parallel axis theorem, all the different pieces, you know, kind of segments down the blade, you could actually physically measure this if you wanted to. You can get an idea of what the moment of inertia will be for all the segments of the blade. And so you can get it right down to where you're actually going to grip the sword. Some other piece of information that are, of course, in these graphs are things like forward pivot point, aft pivot point, vibration nodes. I will cover those a little bit later in this video. What's important to note is that I was able to gather this information for the Norman and have that be fairly similar to sword number 14 in the book. Based on that, and putting that constant of the degrees in there, which was about 17 degrees, I was able to determine essentially what the force was. And I was able to vet this against itself scientifically as a separate process, because I had two processes to gather information. One is the oval. That is directional inertia, so that's linear inertia. And then the cone shape, which represents the rotational inertia. And again, really, really complex thought processes that go behind that. But really what it comes down to is, I believe that they use the exact same amount of force applied to every blade to determine these pieces of information, because kind of working backwards, trying to figure out what that variable actually is, what that constant actually is, by making what's normally a variable a constant, I was able to figure out that it is 0.2, and then the piece of information that's really complex here is it's inertia by radians per second squared. Normally that would be like Newton meters, For something like rotational inertia and even linear inertia, you can do that as like newtons. But I was trying to keep everything similar and very easy to number crunch, and so I didn't want to do a lot of changing to the numbers. But basically what it comes down to is that 0.2 is the force constant for both torque and force. Now torque is force, it's just rotational force, and that's a constant, it's 0.2. And based on that constant, I was actually able to then go back and essentially recreate that graph for number 14 fairly easily, so going back and making that force a constant is key to everything I do in the rest of this process. So that's how I arrived at getting that force number. It's important. It's in there. I actually have a note in one of the links I will be providing, which is the spreadsheet you can do the number crunching. I have a note on the torque and force a constant that basically says, look, I manually figured this out. I reverse engineered it. It was a really complex process, but it gives you the information you need to know to be able to plug in very quickly data about a sword and get these graphs somewhat buildable. So I'm going to describe the process for that now. So there's really three parts to building out these graphs, building out these agility graphs. The first one is just simply taking the measurements. The measurements you need to take in the spreadsheet that I provide in the description are all highlighted yellow. They are the sword mass, the period time average, the center of mass, the axis of rotation, the distance from the center of mass to where your hand would be gripping. The way you would actually want to do that is, again, I'll pick up the Norman here, you'd want to hold it with these like kind of your thumb and your first two fingers, and roughly between those two fingers is where you kind of want to call that the grip. That mostly just has to do with how the math has to work out, and that you have to put a pivot point in there. And when you actually swing a sword, that actually kind of becomes the pivot point, is really those fingers. So keep that in mind. That's where you'll be measuring that pivot point as. Sorry, that distance in terms of the grip. Then you also just need to get some basic information about the sword. Now, I've gone through this process before, and I have talked about it before, and I'm going to pick up my Lichtenauer here because we're going to go through this exercise with my Lichtenauer. I'm going to show you turning this into a graph. So you have the forward pivot point, which is if you hold the blade right here, or the handle right here, and you kind of just rock it back and forth, there's a part of the blade right about here that doesn't really turn as much. It doesn't really shift, so it kind of just rotates on itself. That is both the forward pivot point at the handle as well as the blade. So again, it's actually further down here. I was kind of doing it wrong, but there it is. It's right about there, about midway down the blade. Important to note that this graph will be actually a little bit different from what you'd see in a lot of other swords because this is a practice sword. It actually, a sparring sword, it actually handles a little bit differently, which is pretty interesting when you get the graph actually built. You also have the aft pivot point, which is holding it up near the pommel. This is like a scent stopper pommel, so I held it right where the cord grip actually ends. And you do the same thing. You just kind of rock it back and forth like this, and you'll get a point that doesn't rotate nearly as much, and that's the aft. So the forward and the aft, kind of like ship terminology, but we're using it on a sword. And so you're going to have that for both the grip and for the blade. You'll get those pivot points. Then the other thing you need to get is the vibration points. And this is really, really hard to show on a camera, on video. It's so much easier to see in person. If you were to hit on a vibration note, it's just going to go donk. But if you hit just kind of anywhere on the blade, you'll see that it actually kind of vibrates and wobbles a certain way. And I hope this is apparent enough, but you'll see there's this area right about here where it isn't wobbling nearly as much. And likewise, there's a place that it isn't vibrating nearly as much in the handle, which interestingly enough is right about where you'd be gripping it in a well-made sword. And so you get the general idea of where the vibration nodes are. Again, these are in the graph. With all of that information plugged into this spreadsheet, along with the overall length of the blade. Now, this Albion Lichtenauer, let me actually pull it up here. The overall length is 121 centimeters or that's 1.21 meters. So it's over a meter long. No surprise, it looks like it's over a meter long. But that's really important to get that length measurement, because it is necessary to pull out some other piece of information, such as where certain lengths of the sword are in association to the center of mass. Because the center of mass on a rod is going to be directly in the center, but in a sword, that whole center of mass actually tends to come closer to your I've lost the word. Wow. Closer to your hilt, right? So closer to where you're actually gripping the blade, the sword. And so the blade is actually a good bit lighter, and it pulls everything in closer, and actually what gives the sword agility. If you watch Peter Johnsson's video on this topic, you will see he actually talks about that. A blade is just kind of a hunk of metal until you put those furniture bits on the hilt furniture, and suddenly it becomes a sword, and it adds a lot of the elements that are necessary to give it the agility. With all that information plugged in, you end up with, well, this very, very complex series of numbers, moments of inertia, and all this type of information. But what you end up with is the sword model. And what you have to do is, on the left-hand side, there is the mass location from point of balance, which is center of mass, and you have the effective mass. And so 0 represents that center of mass, and anything negative goes towards the pommel, and anything positive goes towards the tip of the blade. And you have to plug in, you have to kind of figure out what the very tail end of the pommel is in terms of that measurement, that negative number, and you have to figure it out to the tip. So I have these kind of handy dandy things on this 1.21 meter blade at what's essentially 37.5 centimeters from that center of mass to the pommel is the length basically to the pommel. Sorry, and then 83.5 centimeters from that center of mass to the tip of the blade. And so based on that, I can kind of plug it in at the beginning and at the end of kind of this auto-generated list. So I kind of very quickly am able to build the chart, because as soon as I have that in, as you can see here, I have it right here, all this information plugged in. I've changed the two kind of tail end pieces of information because it's not ever going to hit that exact number, but that builds me my graph. And that graph represents the sword. You'll see these graphs at the bottom of things such as the book, and the graphs all kind of differ. Now what's interesting about this graph, about this model, is that, again, it's based on that center of mass. And that center of mass, if it were to keep extending out, it would actually be symmetric. So this is actually a symmetric graph when you look at it. It just goes up and back down. And if it went to infinite, it would just kind of keep tilting out and it'd be symmetric. But what makes a sword different from just a rod, from just a hunk of metal, is that because it shifts things down to one end like this, you actually have it become asymmetric in terms of the weight at the pommel is always a little bit heavier than the weight at the tip in terms of that moment of inertia. And so, it builds this kind of idea of an effective weight, right? You have that effective mass. Really interesting process to kind of just spit that out. Now all the underlying math is in the spreadsheet, so you only have to make updates to the yellow bits, and you can certainly go research, again, the documents I list below, specifically George Turner's research paper on this, because he gives you the steps to go through how you gather this information. You can even check my math. In fact, I would ask you to go check my math, make sure I didn't make any mistakes. I've gone over this for hours and hours and hours. I hope I didn't make any mistakes at this point. It's always possible that I have. It's not always clear, but again, I've been able to generate graphs from this essentially. So that is how you get that effective mass curve that's at the bottom of the graph. So next is then to go in and figure out how to build the inertia concept, both linear inertia and angular inertia, and what that means to make that oval and to make that cone. So that was the bigger challenge, and it's a little bit complex, but we're going to dive right in. So we're going to start with that oval, because the oval is actually the simpler part. When you look at that oval, it took me a while to actually realize why it's an oval. And again, I was able to reverse engineer and get down to that force constant by measuring, literally with a ruler in that book, the length of that magnitude of that oval and kind of comparing it to what it would be in real life, because that's actually what they did in the book. I'm really sure of it at this point. But that oval is an oval because the effective mass of the sword down the length of the blade, which is in this direction. So in the drawing, it'll be in this direction. I have to push all of the mass in that direction. So essentially, if I were to hold this and let gravity do its thing and just hold it, I'd feel the full weight of it. However, if I'm holding the sword this way, and the tip is resting on something, the bit of the weight I'll actually feel isn't the full weight of the sword. And so the vertical part of that oval is actually because it's easier to translate the hilt this way than this way. And wow, it's kind of interesting. Come to think of it, that was actually kind of easier. So that's interesting. When I actually looked to feel for it, now it's only slightly. And in this case, in the case of this blade, the magnitude that I was able to get with that force constant was essentially 12 centimeters by 13 centimeters, a little bit more on both of those. But the X direction is 12 centimeters, so it's harder to push this. So the same amount of force applied to the sword will only move it 12 centimeters, but if I put that force vertically, it'll actually move at 13. So that's the concept behind the oval. When you see that oval in these drawings, that's what it means. It's easier to move it this way than to move it this way. And every sword is like that. Now, it might get closer to looking like a circle. It might even get closer to looking like a really long oval. It just depends on the type of sword and its design. But that's the concept. So easier vertically than horizontally when you're holding the blade in this orientation. What got really complex now is, of course, how that works for the rotational aspect. And essentially what it comes down to is if you know all the information, the period, the time that it takes to move a sword through a pendulum swing, you know the mass, you know the effective mass at multiple locations, which is, let me see here, multiple locations such as, so you need the period of time, you need the inertia from the grip, so where it is on the grip. This is using that parallel axis theorem. As well as some of the other smaller bits of information I'm trying to find here. So you got time, and you have the torque constant, right? So you have that force. If you know those things, you can actually find out what the angular acceleration is, and that angular acceleration is just a radian. So you can actually have an idea of what the overall acceleration will be, and you can represent that as a radian, and you can then take a radian and just convert it to degrees. So if you're really good at math, you can probably visualize what a radian is, but I'm much better with degrees, so I know what 45 degrees is versus 90 degrees and 0 degrees and all that. And I felt that was very necessary because all the tools that I would then use to build these graphs need degrees. So it converts from the angle into radians, and then you can convert the radians into degrees. Again, all that in the spreadsheet I'm providing below. And there you have it. You have the number of degrees. Now, when I did this for the Norman swords measurements, but with number 14, and I did the reverse engineer, and then I removed all the reverse engineering and just used that force constant, I was able to replicate the angle. And then I went through and I did this with my Lichtenauer right here. So as I went through all this information, I found out that this Lichtenauer has an angle degree of 19 degrees. And so that'll be in the graph, 19 degrees. What's interesting about this is when I hold this sword, it's actually got some pretty good point control, but it does take some effort. I went ahead and I did the same process for my dark sword Norman, now ignoring number 14 in the book and just moving on to speak about the actual DS Norman itself, putting it through the same process. I found out that not only is the oval extremely different, in fact almost twice as large on the Y, and about 50% more on the X axis, But I was able to then also get the number of degrees, and it was 22 degrees. So it's actually a little bit more nimble in terms of point control, and getting a cut in there takes less effort. And I believe it. One-handed with this compared to even two-handed with the Lichtenauer, this is super nimble. I have a lot of control with this blade. So I began to sit there and think, okay, I've done all the scientific stuff. Does it actually feel that way? And yes, it does. This is much more nimble, much less effort to move this in different directions, as well as that angular acceleration. And so there you have it. There's the nimbleness of a different sword. So I've done two, and they're kind of vetting out the process. So taking all this information was very time consuming, and again, I'm providing it in the spreadsheet so you can just do it yourself, and all the math is done for you. But the hard part, the very manual part now, is recreating the chart. So I'm going to walk through what that process actually looks like, because it uses software. So in order to generate the graphs, some of it's done for me right here in the spreadsheet I created. It creates the chart for me. I can convert that chart fairly easily over to the graph that I'd be using for visual purposes. Now, all of this is done in a vector style program. I'm using a free one called Inkscape. It's really simple. I'm able to very, very quickly kind of recreate these graphs, relatively speaking. So there's a couple different things I have to do to actually kind of make it look nice. The first one is I just need to go find a picture of the sword I'm doing. So I went to Albion's website, got the full-length profile picture of the Albion Lichtenauer, and pasted it into Inkscape and traced over it with the vector program. So then I was able to have the vector drawing, essentially a very simplified version of the Lichtenauer. Underneath it, I then just took the chart that I built here and I traced it out with the vector program, traced out the chart, and made it into its own little solid object. Then I'm able to go recreate all the little bits and pieces, the forward and aft pivot points, the vibration nodes, the center of mass or the point of balance, putting all that in there. And then I can go in and using this little ruler tool, I can actually scale everything appropriately to get it to what's essentially is millimeters. I'm using everything in basically 1/10 scale, so centimeters becomes millimeters. And I'm able to, get everything scaled properly, so all the drawings will, or all the bits of the drawing will actually be accurate to the scale of what I'm trying to portray. And then I can go in and I can use the ruler tool to build the angles and all of that. And I'm showing it right up here because it's a little bit easier to just show than it is to really describe. But it's this kind of process of setting all the pieces into place, and it took a lot of initial setup because I had to go recreate all the little indicators and drawing points they used in the book. But now that I've got them all created, it's kind of copy and paste. I never really have to do much with it past that initial effort. But here you go. This is the finished chart for the Albion Lichtenauer. And as you can see, it looks very similar to what is actually in the book. So kind of comparing them side by side, they are very similar. And holding it in my hand and thinking about the way this drawing looks, it's pretty accurate, I feel. I compared this chart to some of the other swords in this book, and I'll have to go find it again. But there is one sword that actually looks pretty similar to this one, and it is number 20. So here it is. Here's number 20. And I'll try to get that drawing right up here. Number 20 is called this Zweihander two-hand sword. The dimensions on it are a little bit longer than the Lichtenauer. I believe it's only by just a couple of centimeters, really. And the weight is a little bit heavier, I think, or sorry, a little bit lighter, actually. But it's very similar in terms of its dimensions. And when you look at the way the drawing appears, again, side by side, you can actually see it looks very similar. So I would imagine that the Lichtenauer is actually a fairly good kind of analog for this old museum piece. really fascinating. The blade shape is very similar. Everything is very similar. But I was really looking at the oval and the angle of that cone to figure out if there are any that were similar. And as I went through, I found that one and I looked at it, kind of compared it side by side, and went, huh, very interesting. Some just kind of final notes on all of this. This information is really interesting for sword makers. There's a lot of very, very key elements of what the design of your blade actually does to the handling characteristics of the sword. Now, if I had this blade and I removed mass, either by doing a distal taper, which is changing the thickness or the depth of the blade over time, or if I just did a regular taper and shaved it off more, even if it just comes down to sharpening and removing some metal on the edge, all of that will actually make adjustments and change the handling characteristics. And you can offset changes you make here with changes you can make over here in the hilt components. And so the sword actually becomes something that is, the agility of the sword is something that is completely manipulatable. You as a sword maker, if you are a sword maker, or if you know someone who is, they can actually change the handling characteristics just by taking these models and saying, all right, I need to add a little bit of weight here. What is it going to do to the center of mass? How is it going to change it? How is it going to change the period of the sword as it shifts through the pendulum motion? And based on how all that works, you can actually change the handling characteristics. And you can figure out swords that are analogs for the others. So, very interesting information. Now, some other notes about the Lichtenauer itself in the chart that I have. Normally, where you have that forward vibration node, or that blade vibration node, that also represents, generally speaking, your percussion point. It's not always exactly the same, but generally speaking, that's the range it's going to be in where that vibration is. That means that the maximum transfer of energy from your strike goes from the blade to your target. Anything outside of that kind of general area will actually decrease the amount of that impact. In most swords, it sits in actually a pretty broad range, but it tends to be well above 10%, usually like 15% to 30% of that kind of mass, that moment of inertia actually, that effective mass going from the blade into the target. But it all kind of evens out because it's also the strongest part of the blade in terms of that strike and transferring that energy. What's interesting, I think, about the Lichtenauer is not knowing really what's going to come out of this and doing it on a training sword. I found it really interesting that this training sword, at its kind of general center of percussion area, right, its ideal kind of sweet spot striking range, it's actually transferring a lot less energy. Now, this is going to be very similar from what happens on, say, like a fader, right? Faders still hit really hard, but it's not nearly as hard as it could be. And it's actually true of the Lichtenauer. The design of it, no surprise that coming from Peter Johnsson's designs, the design of it means that it's much safer and less damaging. Even if you're wearing all the jackets, you still get the brunt of that effective mass, but you're getting a lot less of it on something like the Lichtenauer than you would on maybe a sword that's designed more for the cutting and killing aspect. So training sword actually has training sword properties to it. And I think that's really interesting. So this is why I want to use these graphs in my future reviews. And this is, you're going to start seeing this. I'm going to have to rearrange how I do my reviews in order to accommodate them. But I think it's absolutely fascinating. If I had to choose any one thing that I would change about my reviews today, this is it. I need to add these in because you can look at these pictures and begin to get a mental idea of what that sword actually feels like. And even more importantly, the thing I really want to stress is I want to get manufacturers starting to do this, because it's really easy to gather this information and to build it and to display it. I mean, relatively easy. And if manufacturers would show this and say, this is the handling characteristics you can expect in general of this sword design, we could be so much more empowered as consumers to go buy swords that are going to handle really well, or at least handle like we want them to. And I think that's very important. But it's also very important because it will also hold manufacturers accountable for making good swords and not making swords that are in some way inferior because they have terrible handling characteristics. I'm going to be just kind of doing this to my own collection over time, not necessarily building the graphs, but kind of understanding the handling characteristics. I'm really curious, honestly, about the Sword of Rovin that's kind of hiding behind that halberd over there, because it handles terribly. It is a god-awful sword. It feels like a ton of bricks tied to the tip of that thing, and I think it has a ton to do with how it was designed and implemented, and not a lot of thought put into the handling characteristics and making the blade properties and the hilt furniture properties complementary. So I'm going to kind of do that on my own just to figure that out. But I think it's really interesting. I think this is very telling information. That's why I'm presenting it in this really long video, so you can be more informed. And then I would encourage you, go out to your collection and try building these graphs. Feel free to ask me questions. I might even do some more in-depth tutorials on this in the future. But I really just want to get this out there in your hands so you can begin doing it on your own. You can begin researching it on your own, and you can begin to understand what makes a good sword, not just from an opinion standpoint, but from a factual, scientific standpoint. And I think that is a huge, huge deal in just the general sword community. Thank you for watching this incredibly long video. I hope it was informative. I hope it was interesting. I hope I didn't get any of the math wrong. Anyone out there who knows a lot of physics, I apologize, because I know it's an amateur effort on my part. I did reach out to quite a few people to try to gather some information, but I got very few responses back. And so I really ended up having to do this on my own, and I'm just not smart enough to really figure out all the physics for these things. So I did my best. If you have critiques, or you have things that you say, okay, this is wrong, or maybe this is right, please give me that feedback. You can comment here, you can shoot me an email, you can comment directly on my channel, you can hit my Facebook page, you can do all these things, but let me know, because if I need to adjust things, I will adjust them. The document that I have posted below in the description, I will change that if there is new information that comes my way that says I need to change it, so you can go back and get the updated version. So I'm going to kind of keep a revision control on these things. So version 1.0 is below, but if you have information that tells me that I need to make changes, please send it my way. Thank you again for watching, and I hope this was great. See you next time.